A galaxy hovers at the boundary of time itself. Its light has been crossing the cosmos toward us for 13.4 billion years. When it departed, the universe was only 290 million years old, and it had already formed oxygen, something the laws of physics declared could not exist. Scientists named one survey in its honor: Mirage or Miracle. An astronomer at the University of Kansas found herself lying awake at 3 in the morning, asking whether everything she had built her career on was simply wrong. A Nobel laureate announced to the world that what his telescope had uncovered meant, in his own words, "We have misunderstood the universe." If you find that even half as unsettling as we do, stay right here. Like and subscribe, because this story is far from finished. Let's begin. Picture the most distant thing you can conceive, a star so far away that its light departed before our planet was born. A galaxy so remote it occupies the absolute rim of the observable universe. Now, picture finding one that should not exist at all. That is precisely what happened. And it reshapes everything we believed we understood about how the cosmos came to be. December 25th, 2021, Christmas morning. Across the world, children were ripping into gift wrap. Families were settling around holiday tables. And somewhere within that ordinary warmth, a rocket stood on a launch pad cut from jungle in French Guiana on the northeastern coast of South America. Inside its payload fairing sat something that had required 3 decades to construct, had consumed $10 billion, and had shattered the spirit of everyone who built it at least once. The rocket was an Ariane 5. The payload was the James Webb Space Telescope. 7:32 in the morning local time. The count reached 0 and the rocket rose. There were no crowds lining the streets to watch this launch. The people who grasped what was at risk were far too frightened to celebrate. In mission control rooms in Baltimore and Paris and across Europe, engineers sat rigid, eyes locked on monitors, barely breathing. They had devoted years to rehearsing every conceivable failure, every bolt that might snap, every motor that might seize, every circuit that could spark and die. They had catalogued them. 344 single points of failure during deployment alone. 344 moments where one mechanical flaw, one reluctant latch, would terminate the mission permanently. No shuttle could fly out to fix it. No second attempt existed. The telescope was already too far away and pulling farther with every second. The original schedule had called for launch in 2013. Then the mirrors were redesigned. Then the sunshield was redesigned. Then the budget doubled, and doubled once more. Scientists who had devoted their entire professional lives to this machine watched deadline after deadline dissolve. Some retired before it ever flew. One of the telescope's earliest advocates, John Mather, a Nobel laureate who had been working toward this launch since the 1980s, stood and watched the Ariane 5 climb into the sky above the jungle canopy. He did not allow himself to celebrate. Nobody did. The James Webb Space Telescope was Hubble's successor, though calling it that undersells the magnitude of the difference. Hubble works primarily in visible light, the wavelengths human eyes can register. Webb was engineered to capture something older, dimmer, something Hubble could never touch. It was built to receive the very first light ever emitted in the universe. Light so primordial and so attenuated that it had spent the entire age of the cosmos traveling toward us. To accomplish that, the telescope needed to reach somewhere cold and undisturbed, far from the heat and brightness of Earth. Its destination was a gravitational balance point called Lagrange 2, roughly 932,000 miles from Earth on the far side from our Sun. There, a spacecraft can hold a stable orbit, suspended in equilibrium by the combined gravitational pull of Earth and Sun. It is a place of remarkable stillness, and that stillness was precisely what the telescope demanded. 14 minutes after liftoff, the solar panels extended. Power came online. The telescope was alive. But the engineers understood that alive and operational were entirely different things. Ahead lay the most intricate and perilous sequence of maneuvers ever attempted in human spaceflight. And the journey had barely started. Consider what was at stake. Astronomers at universities across dozens of nations had organized entire research programs around data that Webb had not yet gathered. Graduate students had staked dissertation topics on it. The Hubble Space Telescope had notoriously launched with a defective mirror in 1990, but astronauts flew up and corrected it. Webb had no such fallback. Whatever would unfold over the following 29 days was irreversible. There was no repair mission, no emergency patch, no second flight. The rocket was already gone. The telescope was alone, and the gap between it and any human assistance was widening by miles each moment. To grasp what the James Webb Space Telescope is capable of, you must understand its construction and why every design decision was driven by physics itself. Begin with the mirror. 6.5 meters across, roughly the span of a large living room. 18 individual hexagonal segments, each machined from beryllium, chosen for being simultaneously lightweight and dimensionally stable in deep cold. Each segment was then plated in gold, an atomically thin layer selected because gold reflects infrared light better than virtually any other substance. Together, those 18 segments constitute one of the most precisely crafted optical surfaces ever produced by human hands. The tolerances involved would be invisible even under intense illumination. But a 6.5-meter mirror cannot fit inside a rocket fairing. Rockets have fixed diameters, and the mirror is simply too wide. So the engineers designed the mirror to fold. 18. Segments arranged around a central frame and 2 hinged side panels that swing inward like wings folding against a bird's body. The entire structure compresses into a shape narrow enough to fit inside the Ariane 5, then unfurls in space after launch. Nothing of this scale had ever been attempted before. The sunshield presented a different category of engineering challenge. To observe infrared radiation, a telescope must be extraordinarily cold. Any warmth whatsoever, including heat radiating from the telescope's own structure, would corrupt the signal. The instruments required operating temperatures of negative 447 degrees Fahrenheit, a temperature approaching absolute zero, colder than the frozen emptiness between most stars. To reach that, the telescope had to be insulated from every conceivable heat source. Our sun, the reflected light of Earth, even the faint warmth of the moon. The solution was a 5-layer thermal barrier, roughly 69.5 feet long and 46.5 feet wide, constructed from a material called capton. Each layer was aluminized to deflect heat. Think of it as the most sophisticated space blanket ever built, the size of a tennis court and no thicker than a strand of human hair. On the sun-facing side, the shield absorbs intense heat. On the telescope side, the temperature falls to almost nothing. That gradient, spanning just a few inches of layered film, covers hundreds of degrees of temperature difference. Even that was insufficient for one of Webb's 4 instruments. The mid-infrared instrument, which observes the longest wavelengths and therefore the most ancient, most redshifted light in existence, required active cooling, a built-in refrigeration system to drive its detectors to operating temperature. It is among the most sophisticated cryogenic systems ever launched into space. All of this engineering served a single purpose: to capture infrared light. Ancient light. When the universe was young and the first galaxies were assembling, they radiated light at visible and ultraviolet wavelengths. But across the 13+ billion years since then, the universe has expanded. Space itself has stretched, and as it stretched, it elongated those light waves along with it, pulling them from visible wavelengths deep into the infrared spectrum. By the time that primordial light arrives at us, it is entirely invisible to human eyes. Every camera on Earth, every optical telescope ever constructed, cannot detect it. Webb can, because Webb was built precisely to receive it. That is what was folded inside that rocket on Christmas morning. A time machine, a photon collector engineered to receive transmissions dispatched before the Earth formed. Signals stretched and dimmed across 13 billion years of travel. There is something intimate about this, even if it takes a moment to feel it. Every atom of oxygen in your lungs, every atom of iron in your blood was forged in the core of a star that burned and died before our solar system existed. At its most fundamental level, the James Webb Space Telescope was built to trace where all of that came from. The question was whether the messages it decoded would confirm what science already held to be true about the universe, or say something far more troubling. Before the James Webb Space Telescope ever aimed its golden mirror at the cosmos, cosmologists believed they possessed, in broad and confident terms, a working understanding of how the universe operated. That confidence was not hubris. It was earned, assembled piece by painstaking piece across decades of observation, calculation, and experimental validation. The framework they had built was called lambda cold dark matter, and it stood as one of the most successful scientific constructions ever achieved. Here is what it describes. The universe is composed of 3 ingredients, none of them evenly distributed. Only 5% of everything that exists is ordinary matter. Atoms, molecules, everything that comprises stars and planets and oceans, and you. 27% is something called cold dark matter, invisible to light, detectable only through the gravitational influence it exerts on surrounding galaxies. The remaining 68% is even more foreign, a property of space itself called dark energy, which drives the universe's accelerating expansion. Together, these 3 components in those exact proportions reproduce virtually everything astronomers can observe. The model also specified how structure arose. In the earliest instance after the Big Bang, the universe was a near-uniform fog of hydrogen and helium punctuated by tiny fluctuations in density. Gravity acted on those variations. Denser regions pulled in more matter. Over hundreds of millions of years, the fog condensed into the first stars, and those stars coalesced into the first dwarf galaxies, and those dwarf galaxies slowly merged and grew into larger structures, small first, large later. That progression, known as hierarchical structure formation, was among the model's most fundamental and most thoroughly tested predictions. Heavy elements were integral to that story. The early universe held essentially no oxygen, no carbon, no iron, no silicon. Those elements did not yet exist. They had to be forged in the nuclear furnaces of the first stellar generation and then distributed across space when those stars died in supernova explosions. After those explosions, a second generation of stars could emerge, incorporating the debris. Then those died as well, and a third generation formed, chemically richer than either predecessor, each cycle leaving the universe more complex than it found it. Astronomers calculated that accumulating enough oxygen to detect spectroscopically in a distant galaxy required at minimum 1 billion years of stellar birth, death, and recycling. For decades, every observation pointed the same way. The Hubble Space Telescope probed deep space and found exactly what lambda, cold, dark matter, anticipated. The farther back you looked, the smaller and less developed the galaxies appeared. The universe had assembled itself incrementally, the way a city grows from scattered outposts into a thriving metropolis. It was ordered. It was elegant. It was internally consistent. Cosmologists had prevailed. The universe had revealed its architecture. And the architecture matched the theory so precisely that many researchers began wondering whether the grand questions of cosmology might genuinely be resolved within their lifetimes. They were right that answers were approaching. But the answers were nothing like they expected. Consider what that confidence represented. Lambda, cold, dark matter was far more than a classroom theory. It was the organizing framework behind billions of dollars of telescope time, behind every major cosmological survey conducted over the prior 2 decades, behind the professional lives of hundreds of scientists worldwide. If it was seriously wrong, entire research programs would require dismantling. Textbooks would need to be rewritten. The coherent narrative of cosmic history that science had spent 50 years constructing would fracture in ways no one had a blueprint to repair. The Standard Model was the platform on which modern cosmology stood, and Webb, still months from its first scientific images, was about to walk right onto it. 29 days. That was the window in which the James Webb Space Telescope would either become the most powerful astronomical instrument in human history or transform into the most expensive debris ever dispatched to deep space. Deployment began almost immediately after launch. There was no time to mark the successful liftoff, no moment to let the tension exhale. The telescope had to metamorphose from a compressed package inside a rocket fairing into a fully articulated observatory, and it had to do so without a single human hand to guide it. Every step had to execute automatically, driven by preloaded commands sent across distances too vast for real-time intervention. If anything went wrong, the team on the ground could only watch it happen. First came the solar array, extended within minutes of separating from the rocket. Then the high-gain antenna, essential for full bandwidth communication. These early deployments proceeded cleanly. The engineers exhaled, slightly. Then came the sunshield. That vast, gossamer structure, packed into a dense stack for launch, had to be drawn out, tensioned, and separated into its 5 distinct layers, each one stretched across a frame the size of a tennis court. The operation required hundreds of individual mechanical steps, motors drawing cables taut, booms extending outward, membranes pulling flat. Any snag, any tangle, any motor drawing too much current or too little could wrinkle the shield into useless wreckage. For 5 days, the team monitored the shield's deployment, one agonizing increment at a time. It worked. The layers separated. The shield tensioned. The cold side of the telescope began to chill. Next came the secondary mirror, which had to swing outward from its folded position on 3 slender support struts and lock into exact alignment. Then, the 2 wing panels of the primary mirror had to hinge outward. Each hinge had to rotate to precisely the correct angle and lock there permanently. There was no mechanism to rehinge them if they halted short of position. The panel deployments occurred over 2 consecutive days in early January 2022. Controllers in Baltimore called out each latch as it clicked home. A room that had held its collective breath for nearly 2 weeks allowed itself, finally, a few tears. But the telescope was still not functioning. The 18 mirror segments now spread open were each slightly misaligned. Each one had to be individually adjusted using small actuators mounted on its reverse face, nudged by fractions of a millionth of an inch until the 18 separate reflections of a reference star converged into a single, crisp, unified image. That alignment process consumed weeks. Engineers trained the telescope on a bright star designated HD 84406 and watched as the 18 ghost images slowly, painstakingly, drew together into one. March 11, 2022. The final alignment check returned clean. 18 segments had become one mirror, one flawless mirror, colder than almost anything in the natural universe. Parked nearly 1 million miles from home, aimed at the oldest light in existence, the telescope was ready. The universe had no idea what was about to reach it. Reflect on what that alignment actually meant. 18 mirror segments manufactured in separate facilities, transported across the country, folded into a rocket, subjected to the violence of launch, and then sent adrift nearly 1 million miles from any tool or engineer. Through weeks of painstaking remote adjustment, those 18 separate pieces of gold-coated metal became a single, perfect reflector. The precision involved was comparable to aligning a mirror until it could sense the warmth of a candle flame at the distance between Washington, D.C. and Los Angeles. That is the instrument that waited, still and cold, pointed at the oldest darkness in existence. July 12, 2022, the White House held an event. The President of the United States stood before a display and revealed the first official science image from the James Webb Space Telescope to the world. What people saw stopped them cold. A field of thousands of galaxies, each a different color, each a different shape, spirals and ellipses and smeared arcs blanketing a patch of sky so small that a grain of sand held at arm's length would cover the entire area. Every point of light in the image was not a star. Every point of light was a galaxy, holding hundreds of billions of stars. The image reached further back in time than any photograph in history. Scientists and journalists and members of the public stared at it and experienced something that resists easy description. Awe is probably the closest word. A kind of vertigo that comes from understanding, viscerally rather than intellectually, how immense and ancient the universe actually is. The celebration was genuine and widespread. But inside research offices at universities across the country and around the world, some astronomers were studying those early images with deepening unease. Among them was Garth Illingworth, an astronomer at the University of California, Santa Cruz who had spent decades studying distant galaxies and knew better than most what those galaxies were supposed to look like. The earliest galaxies, according to every model, should appear small, disorganized, faint. The universe at that age simply had not had sufficient time to build anything more substantial. What Illingworth and others were seeing in the Webb data did not look like that. Some of those objects appeared unexpectedly large, unexpectedly bright. One word kept surfacing in private exchanges among researchers. Wrong. Richard Ellis, a cosmologist at University College London and one of the most respected observational astronomers alive, was among the first to say it publicly. Studying the early data, he told colleagues, "It worries me slightly that we find these monsters in the first few images." Monsters. It was not hyperbole. These galaxies, if confirmed, were too massive to have assembled in the time available. They violated the chronology of cosmic history the way a fully grown oak tree contradicts any claim that it sprouted from an acorn planted last week. And the Webb telescope, with all its power and precision, had barely begun to look. For the researchers who had noticed the anomalies, there was a disturbing calculation to confront. The sample in those first images was minuscule. Webb had been operational for just a few months. The sky coverage was a fraction of the full observable universe. And yet even within that tiny sample, the data held objects that strained or exceeded the model's limits. If the anomalies were real rather than instrumental artifacts, the statistical implication was stark. Many more such objects should exist across the full sky at every distance Webb had not yet surveyed. The universe might be saturated with early massive galaxies that the standard framework never predicted and could not explain. The first images had been a celebration, but for those who understood what to look for, they had also been a warning. February 23rd, 2023. A paper landed in the journal Nature that shifted the conversation from whispered concern to open confrontation. The authors were Ivo Labe, an astronomer at Swinburne University of Technology in Australia, and Erica Nelson at the University of Colorado Boulder, along with a team of colleagues. They had been analyzing early James Webb Space Telescope photometric data, measuring the light from extremely distant objects, and what they had found was difficult to absorb even for the people who uncovered it. 6 candidate galaxies, all existing between 500 and 700 million years after the Big Bang, with masses that, if the measurements held up, were extraordinary. Up to 100 billion solar masses, 100 billion times the mass of our own star. Some of these objects, if confirmed, would rival the Milky Way in total size. The Milky Way required approximately 13 billion years to build. These candidates had apparently accomplished something comparable in under 1 billion years. Lambda cold dark matter had an explicit prediction for this epoch. Early galaxies should be small. They should be the building blocks, the seeds, the raw material out of which larger structures would gradually be assembled over cosmic time. They should resemble infant clumps of gas and newborn stars. What the data appeared to show instead were fully developed adults sitting in the cosmic nursery with no plausible justification for being there. Joel Laja, a galaxy evolution researcher at Penn State University, read the paper and delivered a judgment that rippled immediately through the astronomical community. These objects, he stated, were in tension with 99% of cosmological models. He did not claim the models were wrong. He said 99% of them could not account for what the data appeared to reveal. Erica Nelson, one of the paper's lead authors, was more direct. "It's just crazy," she said, "that these things seem to exist." The community divided along predictable lines. Established researchers who had built careers on lambda cold dark matter pointed to the error bars. Photometric measurements, they rightly noted, are estimates derived from the color and brightness of light across several wavelength bands, not direct measurements. They could be wrong. They had been wrong before. Redshift estimates obtained this way, called photometric redshifts, had misled astronomers in the past. Perhaps these objects were not as distant or as massive as the data implied. But the data was the data, and there were 6 of them. 6 candidate objects that each individually strained the models, all found in a small early sample before Webb had even begun its systematic deep surveys. The implication, if real, was not that cosmologists had made some minor miscalculation. The implication was that something fundamental about the early universe had been misunderstood. Something about how rapidly matter could self-organize into galaxies, about the conditions that existed during those first few 100 million years. The field had fractured, and the instrument responsible for the fracture was only warming up. Science does not surrender to pressure. It argues back, and in the months after the Labbe and Nelson paper, the arguments came fast and hard, exactly as the process demands. The first line of attack was methodological. Photometric redshifts, critics noted, carry substantial uncertainty. When you measure a galaxy's distance by analyzing how its light is spread across different wavelength bands, you are making an inference built on assumptions about what that galaxy's light profile should resemble. Those assumptions can fail. Dust within a galaxy absorbs blue light and re-emits it as red, making a galaxy appear more distant than it really is. Active galactic nuclei, the energetic cores of galaxies harboring massive black holes, can also inflate apparent brightness, making an object seem far more massive than its stellar content alone would justify. Through 2023, researchers submitted each candidate to rigorous follow-up observation and independent reanalysis. Some did not survive. A handful of the most dramatic early claims were revised downward when better data arrived. The redshifts were less extreme than initially measured. The masses were more modest, still uncomfortably large perhaps, but no longer the catastrophic outliers the first measurements had suggested. The skeptics felt vindicated. The models could breathe again. Scientific social media, to whatever extent that remains a meaningful gauge, declared the crisis overstated. Then came the spectroscopic confirmations, and everything changed again. Where photometric measurements estimate redshift by analyzing a galaxy's overall color, spectroscopy breaks that light into its individual wavelengths and hunts for specific chemical fingerprints. The absorption and emission lines of hydrogen, oxygen, carbon, magnesium. Each element carries a known spectral signature. When you find that signature shifted to longer wavelengths by a calculable amount, you have a precise measure of how fast the galaxy is receding, and therefore exactly how far away it is. Spectroscopy does not estimate. It confirms. The galaxies that survived spectroscopic scrutiny in 2023 were fewer in number than the original photometric candidates. But they were real. Verified not by a single instrument or a single team, but by multiple independent observations, all converging on the same conclusion. These objects existed. They were as remote as the early measurements had suggested. Some were as massive, and none of the counter-arguments could explain them away. What the skeptical campaign had achieved, paradoxically, was to sharpen the problem. By eliminating the candidates that could be accounted for, it left behind precisely the ones that could not. The confirmed galaxies were not outliers sitting at the tolerant edge of what models could accommodate. They were, in the language several researchers used, genuinely anomalous, sitting in regions of parameter space where no galaxy should exist if the standard model was correct. The field had spent a year trying to dissolve the problem. The problem had not dissolved. In some respects, it had deepened. One distinction is worth drawing carefully, because the popular press tends to flatten it. The confirmed anomalies did not mean that all of lambda cold dark matter was broken. The model's predictions about the composition of the universe, the proportions of dark matter and dark energy, remained in excellent agreement with other data sets. The problem was specifically with the timeline of early galaxy formation. How quickly matter organized itself, how fast the first massive structures assembled. On those questions, and only those questions, the Webb data and the model were beginning to diverge in ways a year of critical pushback had failed to resolve. Something real was there. The community was no longer arguing about whether a problem existed. It was arguing about how large the problem was. That is an entirely different conversation. Faced with data that resisted easy explanation, the James Webb Space Telescope science teams did what good scientists always do when confronted with anomalies. They looked harder. The James Webb Advanced Deep Extragalactic Survey, known within the community as JADIS, was the most ambitious imaging and spectroscopic program the telescope would undertake in its early years. The concept was simple, and the commitment was staggering. Point the telescope at two carefully selected patches of sky, regions already studied extensively by Hubble and ground-based observatories, and stare. Hundreds of hours of exposure time, multiple instruments, every photon counted. Kevin Hainline at the University of Arizona led portions of the analysis alongside Stefano Carniani at the Scuola Normale Superiore in Pisa, Italy, and a large international team. Their objective was not to chase individual spectacular objects. Their goal was systematic. Map the galaxy population of the early universe, build a statistically meaningful catalog, measure redshifts not by the dozen but by the thousand, and understand the architecture of cosmic history layer by careful layer, the way a geologist reads rock strata. The survey delivered thousands of cataloged galaxies, with spectroscopically confirmed redshifts reaching back to within the first few 100 million years of cosmic time. JADIS became the deepest and most complete census of the early universe ever assembled. Researchers published paper after paper, each one adding resolution to the picture of how the cosmos had evolved from featureless fog into the structured web of galaxies surrounding us today. Most of what JD's found was consistent with prior knowledge, filling gaps and refining existing measurements. But some of what it found was not. Buried within the vast JADES catalog, sitting at a redshift no one had previously confirmed, was a galaxy that simply did not fit. The data around it accumulated slowly, checked and rechecked by multiple team members who each kept waiting to find the error. There was no error. The object was real, positioned at a distance and a cosmic age that, in the words of several of the researchers involved, should have been physically impossible. The team designated it JADES-GS-Z14-0, and when the announcement of its confirmed properties finally arrived, it surpassed every boundary of what the standard model could explain. It did not merely stretch the boundary, it broke it entirely, in a way that no revision of error bars or alternative interpretation could repair. One of the foundational assumptions of modern cosmology had been tested, and the test had failed. The universe, it emerged, had been far busier than anyone believed it could have been. The catalog entry carrying the designation JADES-GS-Z14-0 was about to become one of the most debated objects in the history of observational cosmology. The team examining its spectral data had already reviewed their work multiple times. They would review it again, and when they finished, the answer would remain unchanged, impossible, and real. May 2024. The confirmation arrived. The galaxy JADES-GS-Z14-0 carried a confirmed spectroscopic redshift of 14.32. That number demands translation to be properly felt. A redshift of 14.32 means the light captured by the James Webb Space Telescope departed this galaxy just 290 million years after the Big Bang. The universe, by the best current measurements, is 13.8 billion years old. 290 million years represents roughly 2% of that total. The universe was, in cosmic terms, a newborn, and this galaxy was already there. That alone was remarkable, but not entirely without precedent for Webb, which had been pushing the redshift record upward since its first science release. What made JD's GS-Z14-0 different was more than the question of when it existed. The deeper shock was what it contained. The galaxy spans 1,600 light-years across. Compare that to the Milky Way, which stretches roughly 100,000 light-years from edge to edge. At 1,600 light-years, JD's GS-CSC sounds modest, but remember the age. At 290 million years, it should not measure 1,600 light-years. It should be a smudge, a protogalactic fragment barely distinguishable from surrounding intergalactic gas. Its stellar mass, approximately 500 million solar masses, was already sufficient to strain models of how quickly gas can collapse and ignite into stars. Then the spectroscopy revealed oxygen. Oxygen does not originate in the Big Bang. The Big Bang produced hydrogen, helium, and trace quantities of lithium, and nothing heavier. Every other element in the periodic table was assembled later, inside stars. Oxygen specifically is manufactured in the cores of massive stars and dispersed into space when those stars conclude their lives in supernova explosions. For oxygen to appear in detectable quantities inside a galaxy, that galaxy must have already hosted at least one, and most likely several, generations of stars that were born, burned through their full stellar lifetimes, and died violently. The Standard Model placed that minimum at 1 billion years. JD's GS-Z14-0 was achieving it at 290 million years. Stefano Carniani, who led the analysis of the galaxy's spectral data, stated the difficulty plainly. How can nature make such a bright, massive, and large galaxy in less than 300 million years? It was not a rhetorical question. He and his colleagues genuinely had no answer. Sander Schaus of Leiden University, working with the same data, offered an analogy. It is like finding an adolescent in a room where you were expecting only infants. The light from this galaxy traveled 13.4 billion years to reach Webb's mirror. Because the universe expanded during that journey, the galaxy now lies at a proper distance of approximately 33 billion light-years from Earth. We are not observing something that exists in the universe as it is today. We are receiving a transmission from a time before our planet, before our sun, before most stars in the Milky Way were born. And that transmission says, we were already here. We had already lived and died and spread our debris across space. Whatever existed before us, you have not yet located it. The question trailing every conversation about JADES-GS-Z 14-0 was always the same. If oxygen was already present at 290 million years, then stars must have formed and ended their lives before we can currently observe what came before. What ignited those first stars? And how much of cosmic history is hidden in a window the telescope had not yet opened? The astronomical community had barely processed the implications of JADES-GS-Z 14-0 when the next discovery arrived. In the weeks following the JADES confirmation, Peter van Dokkum of Yale University and Rohan Naidu of the Massachusetts Institute of Technology announced a separate finding: a galaxy at redshift 14.44. They named it MOM-Z14. The subtitle of their published paper described it, without irony, as a cosmic miracle. A redshift of 14.44 places this galaxy at 280 million years after the Big Bang, 10 million years earlier than JADES-G-S-Z14-0, meaning slightly deeper into the epoch that lambda cold dark matter models understood least. And MOM-Z14 possessed its own constellation of properties that resisted conventional explanation. The galaxy spans approximately 500 light-years, a tiny footprint by any modern standard. But at 280 million years of age, it was not a formless blob of young stars. It was structured, organized. Spectral data revealed a galaxy undergoing an intense burst of star formation, converting gas into stars at a rate that, relative to its size, was extraordinary. And unlike many other anomalous early galaxies, MOM-Z14 showed no evidence of an active galactic nucleus, no energetic black hole artificially inflating its apparent luminosity. The light originated entirely from stars, pure starburst. Lambda cold dark matter's hierarchical formation scenario carried a precise prediction for objects of this type. Massive, structured galaxies do not form early. They form late. They are assembled from the mergers of smaller structures over billions of years. The most massive galaxies in the present-day universe. The giant ellipticals anchoring the centers of galaxy clusters earned their bulk slowly, consuming smaller galaxies across cosmic time. That was how the model worked. Small first, large later, always. MOM-Z14 violated this at every level. Consider a reference point. Sharks have been swimming in Earth's oceans for roughly 450 million years. They predate trees. They survived the dinosaurs. They are, by any biological measure, ancient. MOM-Z14 has existed for 280 million years. This galaxy is younger than sharks. And yet it already displays the structural complexity and chemical signatures that the standard model predicted would take billions of years to develop. The spectral data from MOM-Z14 also disclosed something else. Something that would have seemed beyond reach before Webb began its deep surveys. The galaxy displayed a high nitrogen-to-carbon ratio, a chemical fingerprint that in the present-day universe is associated specifically with the densest, oldest stellar environments in the Milky Way, the globular clusters, those ancient spherical star cities orbiting our galaxy's halo and dating back nearly to the beginning of cosmic time. Finding that signature in a galaxy only 280 million years old suggested that MOM-Z14 was not a primitive ancestor of later galactic architecture. It was already chemically mature in ways the models simply could not accommodate. Van Dokkum, Naidu, and their colleagues were measured in their language. They documented the uncertainties. They acknowledged the need for further observation. But they called it a cosmic miracle, and they meant it in the technical sense, something so statistically improbable under the current framework that its very existence required a new one. Two galaxies, weeks apart, both at the edge of observable time, both impossible under the finest theory humanity had ever built to describe the universe. And the James Webb Space Telescope, hovering nearly 1,000,000 miles from Earth, cooling itself to temperatures colder than open space, had only just started looking. Whatever it found next, the field would never again be able to look at the early universe and claim to understand what had transpired there. The comfortable certainty of lambda cold dark matter was finished. The era of genuine, productive confusion had opened. Confusion in science is not an end point. It is a departure. Every failed prediction, every galaxy that arrived too early, every mass that surpassed what the universe should have permitted, each was an arrow pointing somewhere new. The field had surrendered its certainty. What it received in exchange was a far richer set of questions. One of those questions arrived wrapped in light that had no right to exist. J A D E S G S Z1 3-1 is a galaxy at redshift 13.0, placing it 330 million years after the Big Bang, already deep in territory where lambda cold dark matter struggles. But the redshift alone was not what arrested astronomers. It was the nature of the light the galaxy was emitting. There is a specific ultraviolet wavelength called Lyman alpha radiation. It is produced when hydrogen atoms release energy after absorbing ultraviolet photons from young, hot stars, a signature of vigorous star formation. In the early universe, this signal should be completely invisible to us. The early cosmos was saturated with neutral hydrogen gas, a dense fog extending across billions of light years. That fog is extraordinarily efficient at a single task, absorbing Lyman alpha radiation. Photons at that wavelength enter the fog and disappear. They are captured before they can travel. The standard model of cosmic history was explicit. Any Lyman alpha signal originating before reionization was erased in transit. Period. JADES-GS-Z 13-1 is emitting Lyman alpha. Kevin Hainline of the University of Arizona, analyzing the data, stated it with characterize its understatement. We really shouldn't have found a galaxy like this. That sentence, precise and restrained, carries the full weight of what the detection implies. A signal the fog should have consumed is arriving at our instruments. Somehow the light made it through. Only a few mechanisms could explain this. One possibility is that the galaxy carved out a bubble around itself, a region where the surrounding hydrogen had already been ionized and swept clear, offering the Lyman alpha photons an escape route. But for a bubble large enough to allow this signal to pass to have existed 330 million years after the Big Bang, ionizing radiation would have had to begin burning through the fog far earlier than any model predicted. Another possibility is that the fog was never as dense as the models assumed, that neutral hydrogen density in the early universe was lower, patchier, more locally transparent than the standard timeline permits. Either interpretation leads to the same conclusion. Reionization began substantially earlier than cosmologists calculated. The scale of this revision matters. Every textbook account of early cosmic history contains a timeline for when the universe transitioned from opaque to transparent. That timeline was not a guess. It was derived from decades of observation, cross-checked against multiple independent data sets, and enshrined as one of the firmest chronological anchors in cosmology. JADES Z 13-1 is telling us that anchor is misplaced. What makes this harder to dismiss is its directness. There is no inference chain, no model-dependent calculation interposed between the telescope and the conclusion. The photons arrived. The wavelength was measured. The signal is Lyman alpha from a time when Lyman alpha should not reach us. The universe was not behaving as expected. For the scientists studying these data sets, the question had shifted. It was no longer whether something was wrong with the standard picture. It was how much was wrong, and where exactly the errors had accumulated. Now, consider a different species of wrongness. The problem of observing something directly and still misidentifying its fundamental nature. Before the James Webb Space Telescope launched, Hubble had already produced a discovery that seemed almost impossibly dramatic. Astronomers using Hubble detected a single star at a redshift of 6.2, placing it roughly 12.9 billion light-years away, the most distant individual star ever resolved. They named it Earendel, after a figure from J.R.R. Tolkien's mythology, whose name meant morning star in Old English. The detection relied on gravitational lensing. A massive galaxy cluster between Earendel and Earth was bending and amplifying the light from behind it, the way a cosmic magnifying glass aligned along a path called a caustic can boost a source by factors of thousands. Hubble had caught Earendel riding that caustic. Its light stretched and brightened until a single stellar object billions of light-years away became momentarily visible. It was a genuine milestone. The press announced a record that might stand for years. Then James Webb looked at Earendel. What the telescope found was not what Hubble had implied. The brightness profile and spectral signature of Earendel, analyzed with Webb's vastly superior resolution and infrared sensitivity, matched not a single star but a star cluster. A dense grouping of potentially hundreds or thousands of individual stars packed tightly enough that, at the relevant distances and resolutions, they blur into what appears to be a single point of light. The record for most distant individual star observed may belong to an object that is not a single star at all. Consider carefully what this means for the broader practice of astronomy. The researchers studying Earendel were not negligent. Hubble was performing flawlessly. The analysis was thorough and peer-reviewed. The entire apparatus of scientific scrutiny had examined this object and reached the conclusion. One star. And that conclusion was wrong. If the finest instruments and the most meticulous minds can observe something directly and misidentify its fundamental nature, then every observation becomes a question. Every caption beneath every image, every record claimed, every fact stated with assurance must carry an implicit asterisk. According to what we could resolve at the time, the problem is epistemological, rooted in the nature of knowledge itself, not in any failure of competence. Science has always functioned this way. Each generation of instruments reveals that the previous generation's certainties were approximations. What James Webb is revealing is that some of those approximations were not merely imprecise. They were categorically different from reality. Earendel is not a footnote. It is a lesson about the relationship between observation and understanding. We can aim a telescope at something, measure it with every available tool, name it, celebrate it, publish it in Nature, and still be fundamentally wrong about what we are looking at. That lesson matters, because as Webb continued returning data, it would surface additional cases where the confident conclusion and the actual reality were separated by a gap far wider than anyone had expected. There is a useful analogy here, imperfect as all analogies are. Imagine navigating by starlight at sea, a practice humans trusted for thousands of years. You learn the positions, you plot the courses, you sail with confidence. Then someone hands you a GPS and informs you that the star you trusted most has appeared to shift, that atmospheric refraction had been bending its apparent position the entire time you were using it. Your navigation was internally coherent. Your charts were accurate relative to each other. But your fixed reference point was not where you believed. Arundel is that shifted star. A fixed reference, celebrated and relied upon, that the next instrument revealed to be something other than it appeared. The universe does not dispense clean, simple signals. It offers what it has and leaves the interpretation to us. Every interpretation is provisional. Every record, every headline, every superlative attached to an observation carries an expiration date, measured in the lifespan of the next instrument capable of looking more carefully. Occasionally, science produces a number that becomes load-bearing, a single value upon which so much else depends that if it shifts, everything built on top of it must be reassessed. The Hubble constant is that kind of number, named for Edwin Hubble, who first measured the expansion of the universe in the 1920s. The Hubble constant describes the rate at which the cosmos is currently growing. Measure a galaxy's distance, measure how fast it is receding, divide one by the other. The result, expressed in kilometers per second per megaparsec, tells you how rapidly space itself is stretching. Get that number right, and you can calculate the age of the universe, the pace of structure formation, the ultimate fate of cosmic expansion. Get it wrong, and every model built on top of it is subtly corrupted from within. For decades, cosmologists debated the Hubble constant. By the early 2020s, two measurement methods had emerged as the most credible. They disagreed. The first method looked backward in time. The Planck satellite had mapped the cosmic microwave background, the faint thermal echo of the Big Bang, with extraordinary precision. From those measurements, physicists could calculate the early universe's expansion rate and project it forward to the present day. The Planck result: 67.36 kilometers per second per megaparsec. The second method measured nearby objects directly. Adam Rees of Johns Hopkins University, a Nobel laureate, led a collaboration known informally as the SH0ES team. Supernovae H0 for the equation of state. Using Cepheid variable stars as distance markers and Type 1a supernovae as standard candles, Rios and colleagues measured the current expansion rate from local observations. Their result: 73.04 kilometers per second per megaparsec. The gap between these two numbers is approximately 5 to 6 kilometers per second per megaparsec. That sounds small. It is not small. The statistical significance of the discrepancy had reached 5 sigma. In particle physics, 5 sigma is the formal threshold for declaring a discovery. Inverted, a 5 sigma disagreement between two measurements of the same quantity is the formal threshold for declaring that something may be fundamentally wrong. Some physicists argued the discrepancy reflected a systematic error in one or both methods. Perhaps the Cepheid measurements were contaminated by crowded stellar fields. Perhaps Hubble's resolution was insufficient to isolate individual stars cleanly. That was partly why the James Webb Space Telescope was directed to independently verify the Cepheid measurements. With its far superior resolution, it could separate stars that Hubble had blended and potentially reveal whether the local measurement was inflated by instrumental limitations. In December 2024, Rees's team published their James Webb analysis. The result? 72.6 kilometers per second per megaparsec, within measurement uncertainty, confirming the local value. The measurement error was not the problem. Daniel Skolnick of Duke University responded directly. The Hubble tension was now a Hubble crisis. Ries was precise about what that meant. With measurement errors eliminated, what remains, he said, is the real and exciting possibility that we have misunderstood the universe. 2 independent methods, 2 accurate measurements, 1 universe, 2 different answers. The crisis is real, and it remains unresolved. Here is the question that keeps theoretical physicists awake at night. If the early universe and the late universe yield different expansion rates when probed by independent, verified methods, what does that actually mean? Non-scientists sometimes assume the discrepancy is a technical problem waiting to be cleaned up by better instrumentation. But the instruments have been checked, rechecked, and checked again. Webb has verified the local measurement. Planck's maps of the early universe are the most precise ever produced. The data is not corrupted. The methods are not confused. Something physical is causing the discrepancy. Identifying that something requires choosing among options that each require breaking something the standard model currently considers settled. Option 1. There is unknown physics operating in the early universe. Perhaps in the first few 100,000 years after the Big Bang, some additional energy source delivered the cosmos a brief push, accelerating expansion beyond what the standard model predicts. Mark Kamionkowski of Johns Hopkins University proposed exactly this, calling the hypothetical ingredient early dark energy. The idea is mathematically coherent. If a short burst of extra energy existed in the early universe, it would shift the Planck-derived Hubble constant upward, closing the gap with local measurements. The tension dissolves. The model survives. The problem: early dark energy has never been detected. It leaves no confirmed observational signature. It is a term inserted into an equation specifically because the equation returns the wrong answer without it. Adding undetected physics to resolve a discrepancy is a move that must be made with great care, because at some point a model requiring multiple invisible, unverifiable components ceases to be a model of reality and becomes a sophisticated way of admitting ignorance. Option 2. There is unknown physics operating in the late universe. Perhaps dark energy, the force driving present-day acceleration, is not constant. Perhaps it varies over time in ways the standard model does not accommodate. Some early 2025 data from the Dark Energy Spectroscopic Instrument Survey suggested dark energy might be weakening. If confirmed, that would reshape the late universe expansion history and potentially close the gap from the other direction. Option 3 is the most radical. Perhaps the cosmological principle itself is incomplete. The cosmological principle holds that the universe, at sufficiently large scales, is uniform and isotropic, identical in every direction, with no special axis and no preferred orientation. If that assumption fails, then using an early universe measurement derived under that assumption to predict a late universe measurement becomes formally invalid. The two answers diverge not because something is wrong with physics, but because the universe is not the kind of place the cosmological principle assumed it to be. Each option is serious. Each, if confirmed, would require rewriting chapters of cosmology considered settled for decades. And the honest answer, as of early 2026, is that no one knows which is correct. a deeper discomfort lurks beneath all three options. Every proposed solution to the Hubble tension requires the existence of something not yet directly observed. Early, dark energy is undetected. A time-varying form of late dark energy remains unconfirmed. A violation of the cosmological principle at the required scales is unproven. Cosmology is being asked to choose among three varieties of unknown physics, without sufficient data to definitively eliminate any of them. This is where the question of falsifiability becomes urgent. A scientific model is powerful precisely because it makes predictions that can be tested and, in principle, proven wrong. A model that can accommodate any result by appending additional invisible components is no longer making predictions in any meaningful sense. It is making adjustments. These look similar from outside the enterprise. From within, they are entirely different activities. Cosmologists are acutely aware of this danger. The more honest ones say so directly. The Hubble tension is forcing the field to ask whether it is still doing science the hard way, or whether it has begun doing something more comfortable and less rigorous. Before the confusion over individual galaxies, and before the crisis in expansion rates, there was a process the entire framework of early cosmic history depended upon. It was called Ryanization, and James Webb has fundamentally revised what we believed we knew about when and how it occurred. Ryanization was the great transition. In the first instance after the Big Bang, the universe was a plasma of charged particles opaque to light. Then it cooled. Neutral hydrogen formed. And for hundreds of millions of years the cosmos went dark. No stars, no galaxies, just hydrogen and helium gas drifting in gravitational wells, waiting. This period is sometimes called the Cosmic Dark Ages. Then the first stars ignited. The first galaxies formed. The ultraviolet radiation pouring from those earliest sources began ionizing the surrounding hydrogen gas, breaking neutral atoms back into their component protons and electrons. As ionized bubbles expanded and merged, the fog burned away. The universe became transparent to light. That transition from opaque to clear is Ryanization. The established timeline placed its beginning around 400 to 500 million years after the Big Bang, with completion by roughly 1 billion years. This was not a rough estimate. It had been derived from observations of distant quasars, confirmed by Planck satellite data, and embedded in the Standard Model as one of its most reliable chronological anchors. James Webb's observations have torn that timeline apart. Charlotte Mason of the University of Copenhagen, one of the field's leading Ryanization researchers, described the community's reaction with characteristic understatement. Everyone was freaking out. The Lyman alpha detections from galaxies like JADES-GS-Z13-1, combined with the sheer number of bright, energetic galaxies found in the first 500 million years, all converge on the same conclusion. Reionization was clearing regions of the universe far earlier than predicted. The process was operating faster than models permitted. By how much? A 2024 paper in the monthly notices of the Royal Astronomical Society, one of the oldest and most respected journals in astronomy, put a number to it. Reionization concluded approximately 350 million years earlier than models had predicted. And then it went further. The paper stated directly that the lambda-cold dark matter timeline simply cannot accommodate the combined James Webb and Planck observations, even if exotic corrections are applied. That final clause is significant. Even with exotic corrections, the authors were not saying the model required adjustment. They were saying the model's timeline was incompatible with observation at a level that no adjustment could bridge. 350 million years earlier in a universe 13.8 billion years old may sound like a modest correction. But those 350 million years are not drawn from the middle of cosmic history. They are drawn from the very beginning, the first sliver of the universe's existence, when conditions were most extreme, and the foundational processes that shaped everything thereafter were operating at full intensity. Getting that window wrong by 350 million years is not a small error in a large number. It is a large error in the most sensitive, most consequential interval in cosmic history. The data kept arriving. The anomalies kept accumulating. And somewhere in the midst of it, the human dimension of this upheaval became visible in a single remark from a working scientist. Alison Kirkpatrick is a professor of astronomy at the University of Kansas. She has devoted her career to studying galaxies in the early universe. She was trained in the framework of lambda cold dark matter. She taught it to her students. She constructed her research program on its predictions. In that sense, she represents an entire generation of cosmologists who entered the field when the Standard Model felt solid, who invested their most productive years in extending it, and who are now watching its foundations tremble. In 2023, Kirkpatrick said this: "Right now, I find myself lying awake at 3 o'clock in the morning, wondering if everything I have ever done is wrong." That sentence landed differently for scientists than for the general public. For non-specialists, it reads as a moment of private doubt. For anyone who understands what it means to construct a career in theoretical science, it reads as something closer to vertigo. Consider the path that led to Kirkpatrick lying awake. Years of graduate school absorbing the mathematics and observational methods underpinning the Standard Model. A dissertation, postdoctoral positions, a faculty appointment won in fierce competition, courses designed and delivered, graduate students mentored, papers published, grant applications written, reviewed, funded, an entire professional identity assembled around a specific picture of how the universe works. And then the data begins, saying that picture is wrong. The weight of that is real. It carries grief. The loss of certainty in something you have staked years on is genuinely painful. Some of that is ego, but much of it is simply the disorientation of discovering that the map you have been using to navigate does not match the territory. It also carries something else. Kirkpatrick has spoken publicly about the anxiety, but also about something she did not anticipate: the exhilaration. Because if the map is wrong, the territory is more interesting than anyone knew. The career you believed you had, exploring the familiar corners of a mostly understood universe, turns out to be something far more open, far more uncertain, far more alive. That is science operating exactly as it should. The discomfort is not a failure of the system. It is the system functioning correctly, generating data that challenges assumptions, forcing revision, producing the productive disorientation that precedes genuine understanding. But on a purely human level, it is still frightening. To lie awake at 3 in the morning, questioning whether your map of reality requires redrawing, is not an abstract philosophical exercise. It is something you feel in your body. Kirkpatrick's sleepless nights are not hers alone. They belong to an entire generation of scientists living through the most significant revision of cosmological understanding in decades, who must do so while teaching, publishing, and advising, continuing to function as though the ground beneath them is firm, even as they watch it shift. there is a specific class of mystery that exposes the limits of human pattern recognition. James Webb has produced one of the finest examples of it in modern astronomy. Scientists called them little red dots. The name is accurate and unadorned. When Webb's first deep-field images returned, a new population of compact, extremely red objects appeared distributed across the early universe, clustering in the first billion years of cosmic history. They were small. They were bright, they were very, very red, and they fit no existing category. By 2024, 341 of them had been catalogued. Over the following 3 years, the scientific community advanced 4 distinct explanations for what they were. Each ran into serious trouble. In 2022, the leading hypothesis was that little red dots were compact starburst galaxies, extremely dense pockets of furious star formation whose ultraviolet emission had been redshifted into the infrared by the expansion of the universe. It was a reasonable first guess. Spectroscopic analysis refuted it. The spectral signatures did not match. Between 2023 and 2024, attention shifted to active galactic nuclei. Galaxies harboring supermassive black holes at their centers that were actively accreting gas and radiating enormous energy across the electromagnetic spectrum. Actively feeding black holes are X-ray emitters. They produce X-ray signatures as a reliable byproduct of accretion. If little red dots were active galactic nuclei, they should appear in X-ray surveys. Of 341 catalogued objects, exactly 2 were detected in X-rays. 2. That hypothesis collapsed. In September 2025, a third theory emerged. Black hole stars, a theoretical class of object in which a black hole forms the gravitational core of an immense ball of gas, powering the entire structure from within. Objects of this type had been theorized but never observed. The hypothesis remains unconfirmed. Then, in January 2026, 2 independent papers arrived simultaneously from opposite sides of the Atlantic, and they disagreed with each other. A team at the Niels Bohr Institute in Copenhagen published in Nature. Little red dots are young black holes enveloped in cocoons of dense ionized gas. The cocoon absorbs and reprocesses radiation, explaining both the extreme redness and the absence of X-ray signatures. The same week, researchers at the Harvard-Smithsonian Center for Astrophysics published their analysis. Little red dots may be supermassive stars of approximately 1 million solar masses each. Metal-free objects of a type never directly observed, sometimes theorized as precursors to the first supermassive black holes. 2 papers, 2 research teams, 2 entirely different identities for the same population of objects. No consensus, 4 theories, 3 years, 341 unexplained objects. The scientific process is working. Each wrong answer narrows the search space. But every time the field believed it had arrived at a solution, the universe disagreed. Consider the human scale of this failure to converge. Hundreds of researchers across dozens of institutions have devoted years to these objects. Graduate students have written dissertations about them. Observing time on the most expensive scientific instrument ever built has been allocated to their study. Peer-reviewed papers, each representing months of analysis and careful argument, have proposed and defended each successive theory. The community is not failing from lack of effort or expertise. It is failing because the objects themselves do not fit the categories that existing physics constructed. That is what a genuinely new phenomenon looks like in real time. Not a clean discovery with a press release and a Nobel Prize waiting at the end of a tidy, logical chain. It looks like this: 4 years of increasingly confident wrong answers, 2 simultaneous and contradictory correct answers, and 341 objects sitting in the data refusing to be categorized. What James Webb has demonstrated through the little red dots is that the early universe was doing something with its mass and energy that no living physicist anticipated. That realization carries a weight that numbers and press releases cannot fully convey. While astronomers were cataloging little red dots and measuring expansion rates, a quieter anomaly was accruing in a separate dataset, one that, if confirmed, would demand revising something even more fundamental than the Ryanization timeline or the masses of early galaxies. It would require revising the most basic assumption cosmology makes about the nature of reality itself. The cosmological principle holds that the universe, at sufficiently large scales, is isotropic and homogeneous. Isotropic, it appears identical in every direction. Homogeneous, its properties are uniform everywhere. There is no privileged location in the universe, no special axis, no preferred orientation. The universe, observed from far enough away, has no handedness. This principle is not a philosophical preference. It is the mathematical substrate beneath the Standard Model. The equations governing cosmic evolution, including those from which lambda cold dark matter is derived, assume isotropy. Remove that assumption, and the entire formal structure must be rebuilt from different initial conditions. Then astronomers analyzed the rotation directions of the earliest galaxies in the James Webb Advanced Deep Extragalactic Survey, and the numbers came out strange. Galaxies, like storms and planets, can spin in either direction. In a universe with no preferred axis, those rotations should be distributed randomly, roughly half clockwise, roughly half counterclockwise. Lambda cold dark matter is explicit. The ratio should be 1:1. Among the earliest surveyed galaxies, approximately 2/3 appeared to rotate clockwise, a 2:1 ratio. If that finding is confirmed through further observation and independent analysis, the implications are severe. A 2:1 preference for clockwise rotation in the earliest galaxies would mean the universe inherited a directional bias from the Big Bang itself. The cosmos would have a memory. It would have, in the most literal possible sense, a handedness. Scientists are appropriately cautious. The sample size is not yet sufficient to constitute a definitive discovery, and systematic errors in measuring rotation directions at cosmological distances are real and non-trivial. Independent confirmation is required before firm conclusions can be drawn. But the finding is being taken seriously, and if it holds, it does not merely append another anomaly to the growing list. It calls into question whether the cosmological principle, the theoretical foundation underlying every other framework cosmologists have used to analyze every other anomaly on this list, is actually true. To understand why this matters so profoundly, consider what the cosmological principle does for cosmology. It functions as far more than background scaffolding. It is the license that permits scientists to extrapolate from local observations to universal conclusions. When a cosmologist measures the expansion rate in one corner of the sky and declares it representative of the universe as a whole, that extrapolation is valid only if the universe is genuinely the same in all directions. If it is not, if it carries a preferred axis, a memory of its initial conditions, then every such extrapolation becomes suspect. The measurements remain accurate. The conclusions drawn from them, however, may not. A universe with handedness would be a universe that remembers its birth. That memory would be encoded in the rotation of the first structures to form, transmitted across billions of years of cosmic evolution, visible today in the spin directions of galaxies condensed from those original asymmetric conditions. It would mean the Big Bang was not perfectly symmetric. It would mean the universe we inhabit has an orientation, a direction it leans, inherited from a beginning less uniform than the standard model requires. And it would mean that cosmology, for all its precision, has been calculating on a foundation it assumed was level without ever directly verifying that assumption. Faced with all of this, a significant group of cosmologists has pushed back, forcefully, intelligently, and they are worth hearing. The case for lambda cold dark matter is not merely the case for a theory that refuses to yield. It is the case for a model that has successfully predicted and explained an enormous range of phenomena across billions of years of cosmic history. The temperature fluctuations of the cosmic microwave background, the large-scale structure of the universe, the distribution of galaxy clusters, the abundance of light elements produced in the first minutes after the Big Bang. Across all of these measurements, lambda cold dark matter performs extraordinarily well. That record does not evaporate because Webb found some unexpectedly large galaxies. The defenders of the standard model advance several serious arguments. First, stellar mass estimation in the early universe is genuinely difficult. The techniques used to infer mass from the light of early galaxies require assumptions about dust content, star formation history, and stellar population that introduce real uncertainties. Some of the most alarming early mass estimates may be systematically inflated. Second, active galactic nuclei contamination. Feeding supermassive black holes can outshine the entire stellar content of their host galaxy by orders of magnitude. If a massive early object contains a bright, unaccounted-for AGN, its apparent stellar mass will be dramatically overestimated. Several of the most concerning cases of early massive galaxies have, on closer examination, shown AGN signatures. Third, selection bias. Webb was built to detect the brightest, most luminous objects at high redshift. Bright, luminous objects are by definition extreme outliers of any distribution. Lambda cold dark matter permits some fraction of unexpectedly massive early galaxies. If Webb is pointing at those exceptional objects because they are the only ones bright enough to detect, the survey may be constructing a portrait of the early universe from its rarest specimens. Garth Illingworth of the University of California, Santa Cruz, one of the most experienced galaxy observers alive, framed his own puzzlement honestly. How do you do this in the universe at such an early time? How do you form so many stars so quickly? His question is genuine. It is not dismissal. It is a scientist confronting data that surprises him and asking the correct question. These arguments are serious. They are offered by serious people, and for each individual anomaly, they provide at least a plausible path toward reconciliation with the standard model. The difficulty is that the anomalies are not arriving individually. They are arriving together, from independent observations using independent methods, all pointing the same direction. For every galaxy whose mass the defense explains away through dust corrections, a new one appears that resists that explanation. For every mass estimate contaminated by an AGN, another galaxy sits with no such contamination and still too much mass. The individual rebuttals are credible. The cumulative pattern is harder to set aside. 40 years is a long time to be ignored. Or rather, 40 years is a long time to be right and find no one willing to listen. In 1983, an Israeli physicist named Mordechai Milgram published a paper proposing something radical. He was addressing an observation that had been troubling astronomers for years. Galaxies rotate at speeds that should, under the gravity laws then understood, cause them to fly apart. Their outer regions move faster than the visible mass can explain. The standard resolution, which became the central assumption of lambda cold dark matter, was that invisible dark matter provides the additional gravitational pull. Milgram proposed something different. Rather than adding invisible matter, he proposed modifying the law of gravity itself. Specifically, he proposed that at very low accelerations, far below anything experienced anywhere in the solar system, gravity does not obey Newton's inverse square law. It falls off more slowly with distance. The result? The outer regions of galaxies feel more gravitational pull than standard Newtonian dynamics would predict, with no dark matter required. He named the framework Modified Newtonian Dynamics, or MOND. For the next 4 decades, mainstream cosmology largely ignored it. Lambda cold dark matter was too successful. It matched the cosmic microwave background. It reproduced large-scale structure. Dark matter was the accepted solution, and MOND was treated as a curiosity, a framework that might explain rotation curves but stumbled on larger-scale phenomena. It was pushed to the margins, cited mainly by a small community of researchers who continued refining it while the rest of the field moved on. James Webb changed the calculation. The galaxy rotation anomalies observed in early universe surveys. The failure of dark matter simulations to reproduce the number, mass, and architecture of early massive galaxies. The reionization timeline crisis. All of these are problems for a dark matter framework. MOND predicts some of them naturally, without hypothetical particles that have never been directly detected, despite decades of searching in underground laboratories and particle accelerators. This does not mean MOND is correct. Its own unresolved difficulties are real. It struggles to explain galaxy cluster behavior without invoking some form of supplemental mass. It lacks a fully relativistic formulation testable against the cosmic microwave background with the same precision as lambda cold dark matter. There are observations it does not explain as cleanly as its advocates would prefer, but a theory that spent 40 years in the scientific wilderness is suddenly, undeniably, back at the table. Researchers who were once told they were wasting their time are now being invited into collaborations. Their predictions are being tested against Webb data with genuine openness. The era of dismissal is over. What does it mean when a marginalized alternative turns out to have been pointing toward something real? It means the mainstream was wrong to dismiss it. It means the social architecture of science, the prestige hierarchies, the funding structures, the publication incentives that collectively determine which ideas receive resources and which are left to starve. Failed for 40 years. It failed Milgram and everyone who worked on MOND. The ideas survived anyway, sustained by a small community operating at the field's periphery, waiting for data that would compel the center to listen. The James Webb Space Telescope did not vindicate MOND, but it forced cosmology to stop pretending the alternative did not exist. While the field was being compelled to reckon with a long-dismissed alternative, something else was unfolding inside the mainstream. The theorists had not been passive. While critics sharpened their arguments, a separate group of physicists had quietly assembled a repair kit for lambda cold dark matter. The kit had a name: early dark energy. And the moment you understand what it actually is, one unsettling question comes into focus. At what point does repairing a model become abandoning it? Mark Kamionkowski at Johns Hopkins University developed the proposal with colleagues in the years leading into the 2020s. The logic was this: the Hubble tension, that persistent disagreement between the expansion rate measured from the ancient cosmic microwave background and the rate measured from nearby galaxies, could theoretically be resolved if the early universe contained an additional form of energy, something that existed only briefly, shortly before the formation of the first atoms. A brief surge of repulsive energy that slightly accelerated expansion during those first 380,000 years, then vanished completely, leaving no trace behind. If such a surge existed, the cosmic microwave background measurements would yield a marginally different Hubble constant, one that, once adjusted for the early boost, reconciles with the higher local measurements. The tension dissolves. The model survives. The physics community received early dark energy with cautious interest. Some papers found it plausible. Some found it promising. The Hubble tension was genuine, and this was at least a structured response to it. But then came the harder question, the one with no clean answer. Has anyone ever detected early dark energy? No, it has never been observed. There is no direct evidence it exists. There is no predicted signature that has been confirmed in any dataset. Early dark energy is inferred from the gap between two numbers that refuse to agree. It is, in the most precise scientific sense, a postulate invented to preserve an existing framework. Here is where the discomfort becomes structural. Lambda cold dark matter already requires two undetected, invisible ingredients: dark matter, accounting for 27% of the universe's mass energy, has never been directly observed in any laboratory on Earth. Dark energy, accounting for 68% of everything, is inferred entirely from the accelerating expansion of space, and its physical nature remains completely unknown. Ordinary matter, everything you can see, touch, or measure directly, constitutes only 5% of what lambda cold dark matter describes. Add early dark energy, and the model now requires three separate, undetected components, three invisible pillars holding up the architecture. Each is individually scientifically defensible. The indirect evidence for dark matter is substantial. The case for dark energy is real. Early dark energy at least addresses a genuine anomaly. But stepping back and viewing the structure as a whole, something uncomfortable crystallizes. A model that explains the universe almost entirely through ingredients that cannot be directly detected or characterized is a model that is very difficult to falsify. And a model that cannot be falsified is, at some level, a model that cannot be tested. That is not a reason to abandon lambda cold dark matter. It is a reason to take seriously the question of what scientific explanation actually means. Kamionkowski and his colleagues understand this. They are not naive about the epistemological weight of what they have proposed. The field knows it. In the background of every workshop and conference where early dark energy is discussed, the same tension is present. Patching a model is legitimate science until the patches outnumber the original structure. At that point, you are no longer defending a theory. You are constructing a replacement piece by piece while calling it the old one. The question the field has not answered is simple. How many patches are too many? Set aside the mainstream patches for a moment. Because on a different shelf of the same theoretical library, a stranger hypothesis has been gathering adherents. one that begins with a deceptively simple question. What if the universe did not wait for stars to die before producing its first black holes? The conventional picture of black hole formation runs through stellar death. A massive star exhausts its fuel. Gravity wins. The core collapses. A black hole forms. It is a process measured in millions of years of stellar evolution. Lambda, cold dark matter, predicts that the earliest black holes formed this way, then grew gradually by consuming surrounding material across billions of years. But James Webb keeps finding supermassive black holes in the earliest epochs of the universe. Black holes containing hundreds of millions or billions of solar masses, already fully developed in a universe only a few 100 million years old. The standard formation pathway cannot produce objects that massive that quickly. The numbers simply do not add up. The primordial black hole hypothesis offers a radically different origin story. In the first fractions of a second after the Big Bang, space was not smooth, was violently uneven, saturated with regions of extreme density, fluctuating against regions of relative emptiness. Scientists theorize that wherever density fluctuations surpassed a critical threshold, gravity overwhelmed the outward pressure of the newborn universe and collapsed those regions directly into black holes. No stars required, no stellar evolution, no waiting. These primordial black holes would have existed from nearly the very beginning. Their masses could span an enormous range. Some theoretical estimates permit primordial black holes as light as a fraction of a gram. Others, formed from larger density fluctuations, could have carried masses millions of times that of our Sun from the instant of formation. If the most massive primordial black holes existed early enough and in sufficient numbers, they would have served as gravitational scaffolding. Matter falling toward them would feed the black holes, but it would also pile up in surrounding halos, compressing gas, and triggering star formation at rates that standard models cannot produce. The result would be galaxies assembling far faster than lambda cold dark matter's hierarchical model allows, exactly the kind of galaxies Webb keeps finding. The hypothesis extends further. Primordial black holes within certain mass ranges could also contribute to the dark matter budget. If enough formed with masses in the appropriate range, they would behave gravitationally like dark matter, clumping, attracting ordinary matter, bending light without emitting any detectable radiation. Some researchers have proposed that primordial black holes in a specific mass window could constitute a meaningful fraction of the dark matter lambda cold dark matter requires but cannot identify. Avi Loeb at Harvard has been among the more vocal proponents of taking this hypothesis seriously as an observational target. Others in the field are more cautious, noting that constraints from gravitational microlensing and the cosmic microwave background have already ruled out primordial black holes as the dominant form of dark matter across most mass ranges. The hypothesis remains genuinely unconfirmed and genuinely unrefuted. Primordial black holes have not been directly detected, but no observation has conclusively eliminated them either. And, given that Webb is finding objects that no other hypothesis explains cleanly, the idea that the universe seeded itself with black holes before the first stars ignited has graduated from fringe speculation to serious scientific contention. What would it mean if they exist? It would mean the universe arrived pre-structured, pre-wired, with gravitational seeds from its very first instance. It would mean the architecture of everything visible, every galaxy, every cluster, every filament, traces back to turbulence in the first fraction of a second of existence. That is either an answer or the opening of a far deeper question. Step back. Step all the way back. Set aside the specific anomalies, the early galaxies, the Hubble tension, the spinning clusters, and ask a question that cuts across all of science. What has it actually taken for a great theory to fall? The historical record, examined carefully, reveals that the answer is almost never a single devastating experiment. It is almost never that clean. Great theories fall slowly and then suddenly. Consider Newton. Newtonian gravity was the most successful scientific theory in human history at the height of its dominance. It predicted planetary orbits with extraordinary precision. It explained the tides. It powered the industrial age. Then astronomers applied it to Mercury. The planet nearest our Sun orbits in a path that deviates slightly from Newton's prediction. The discrepancy is tiny, only 43 arcseconds per century. A number so small it sounds like a rounding error, but it was real and reproducible, and no adjustment to Newtonian mechanics could eliminate it. It took 40 years of discomfort before Einstein's general relativity arrived to explain it. Consider the static universe. Before Edwin Hubble's redshift measurements in the 1920s, the dominant assumption was that the cosmos existed in a permanent, unchanging state. Einstein himself inserted a cosmological constant into his equations specifically to prevent his own theory from predicting an expanding universe, because the notion was conceptually uncomfortable. Then Hubble published his data. The universe was expanding. The static model did not yield gradually. It collapsed overnight. Consider the steady-state model of the 1950s, championed by brilliant physicists including Fred Hoyle, who argued that the universe had no beginning, that matter was continuously created to maintain constant average density as space expanded. The steady-state model possessed genuine predictive power and elegant simplicity. It died when Arno Penzias and Robert Wilson detected the cosmic microwave background radiation in 1965, the afterglow of a hot, dense beginning that steady-state cosmology had no room to accommodate. The pattern across all three episodes is identical. The anomalies were present for years, sometimes decades before the paradigm shifted. The defenders of the old models were not incompetent. They were often the most rigorous scientists in their fields, pressing hard for explanations that had performed brilliantly before. The shift came when the weight of unexplained observations reached a threshold that no patch could address. Lambda cold dark matter has survived prior challenges: the missing satellites problem, the too big to fail problem. Various tensions between simulations and observations that were eventually resolved through better modeling of baryonic physics. The model adapted. The model endured. But the rate of anomalies emerging from Webb is qualitatively different from anything in recent memory. In the first 3 years of scientific operation, the telescope has generated more significant challenges to the standard cosmological model than the entire preceding decade of combined observations. The anomalies are not concentrated in one domain. They span galaxy formation, black hole growth, chemical evolution, the expansion rate, and large-scale structure. They emerge from different instruments, different research groups, different methodologies. History suggests the model will likely survive. But history also tells us that when anomalies are sufficiently varied, sufficiently consistent, and sufficiently resistant to individual explanation, the model that survives does so by becoming something fundamentally different from what it was. The question is not whether lambda cold dark matter will change. The question is how much. The press releases always read the same. Confident language, carefully hedged conclusions. Scientists speaking in the passive voice about what the data suggests, what the observations are consistent with, what requires further study. The public face of cosmology in 2026 is composed and calibrated, projecting the image of a field managing complexity in an orderly fashion. Attend the conferences, read the working papers, talk to researchers off the record. A different picture emerges. The field is not unified. It is not quietly confident. Inside the community, there is a real and widening distribution of opinion about what Webb's findings mean and where cosmology currently stands. One group, probably still the majority, believes lambda cold dark matter will endure. Their argument is not complacency. It is historical track record. The model has absorbed challenges before, each time through improvements in simulation fidelity and better understanding of star formation physics. The early galaxy anomalies, in this view, reflect the complexity of gas dynamics and feedback processes in the early universe, not a failure of the underlying cosmological framework. These researchers are not dismissing Webb's findings. They are betting that sufficient computational refinement will reconcile simulations with observations. A second group believes lambda cold dark matter requires fundamental revision rather than incremental refinement. These researchers point to the number, variety, and consistency of the anomalies as evidence that the model's core assumptions, not merely its secondary parameters, are under strain. They are not predicting imminent revolution. They are arguing that the field must seriously investigate modifications to the dark matter prescription, alternatives to cold dark matter, and potentially revised treatments of how dark energy behaves across cosmic time. A third group, smaller but growing, employs a phrase that mainstream cosmology tends to avoid: paradigm shift. These researchers argue that the accumulation of Webb anomalies, taken together with the Hubble tension and the large-scale structure discrepancies, points toward a fundamental incompleteness in the current model, one that cannot be patched and can only be replaced. What is striking about this distribution is the size of the uncertain middle. A large fraction of working cosmologists, when asked privately, do not know which camp is right. They are genuinely uncertain. They continue to publish, to refine, to work within lambda cold dark matter, because that is the framework that provides tools, predictions, and community. But the certainty that characterized the field following the cosmic microwave background measurements of the early 2000s has quietly eroded. One senior cosmologist, speaking at a workshop in 2024, stated it plainly. The data is telling us something. We don't agree on what. That kind of honesty is not weakness in a scientific community. It is precisely the condition that precedes a productive reckoning. The consensus is not cracking dramatically. It is developing fissures, fine lines running through conference rooms and seminar halls and private email threads across the field. None has become a break yet, but each new Webb data release applies pressure to the same places. Fissures under sufficient pressure become fractures. Here is a question that sounds straightforward until you attempt to answer it precisely. How old is the universe? Ask a physicist in 2005 and they will respond with calm assurance. 13.7 billion years, plus or minus a small margin. Ask one in 2026, and the honest answer has grown more complicated. The figure on paper is 13.8 billion years, derived from lambda cold dark matter's best fit to cosmic microwave background data. But behind that number is a chain of assumptions, and Webb has been pulling on several of those links simultaneously. The problem begins with the Hubble constant. If the universe is expanding faster than lambda cold dark matter predicts, as local measurements increasingly suggest, then running the expansion backward to find the beginning produces a shorter timeline. A higher Hubble constant means less time since the Big Bang. Some estimates consistent with local measurements place the universe's age closer to 12.5 or 13 billion years, not 13.8. That alone would be consequential. But Webb introduced a second layer of complexity. The telescope has observed ancient globular clusters, dense, spherical gatherings of hundreds of thousands to millions of stars that formed in the earliest epochs of galaxy formation. Some of these clusters, when their stellar populations are analyzed, appear extraordinarily old enough that their apparent ages under certain measurement approaches approach or conflict with the 13.8 billion year figure. A universe cannot contain objects older than itself. If globular cluster ages are being measured accurately, and the universe is as young as the high Hubble constant implies, the accounting does not balance. One proposed resolution is deeply unconventional. A paper in the monthly notices of the Royal Astronomical Society advanced what its authors called the covarying coupling constants plus tired light model. Under this framework, fundamental physical constants differed in the early universe, and light loses energy traveling across cosmic distances through a mechanism distinct from the redshift caused by expansion alone. The model's authors argue it accommodates the Webb observational data more naturally than lambda cold dark matter, and their estimate for the age of the universe is 26.7 billion years. Mainstream cosmology does not embrace this. The covarying coupling constants plus tired light model is considered fringe by the overwhelming majority of working cosmologists. Standard tired light theories have been eliminated through multiple independent observations. But the paper was peer-reviewed, published in a major journal, and its authors argued their modified version addressed the traditional objections. The significance is not that 26.7 billion years is correct. The significance is that the age of the universe, which most people assume is a settled question, is currently a subject of genuine scientific dispute in a way it has not been for more than 3 decades. Textbooks present 13.8 billion years as established fact. The research frontier presents something messier. When the answer to how old the universe is depends on which data set you trust, and different data sets keep disagreeing, the question is open. There is a number that appears in nearly every lambda cold dark matter summary, without much comment. 27%. That is the fraction of the universe's total mass energy attributed to dark matter. Not ordinary matter, but something else entirely, something no instrument ever built has directly detected. Physicists infer dark matter's existence from its gravitational effects. Galaxies spin too fast for their visible matter alone to hold them together. Galaxy clusters deflect light by amounts far exceeding what their visible mass could produce. The large-scale structure of the cosmic web, the filaments and voids spanning hundreds of millions of light-years, only emerges in computer simulations when dark matter is included. The indirect evidence is strong. The cumulative case is genuinely compelling. But Webb has been straining the simulations that use cold dark matter to generate those structures. Cold, dark matter by definition moves slowly. It clumps readily at small scales. It builds structure from the bottom up, small halos merging into larger ones across billions of years. Lambda cold, dark matter's hierarchical formation model predicts a specific distribution of galaxy sizes and masses at different epochs of cosmic history. The galaxies Webb is finding at redshifts above 10 do not match that distribution. They are too massive, too structured, too chemically evolved for their age. The simulations that use cold, dark matter as their scaffolding cannot reproduce them. Researchers have spent 3 years asking whether improved stellar physics can close the gap. Some of it can, not all of it. 3 explanations are currently in circulation. First, cold, dark matter is correct, and the discrepancy lies entirely in the baryonic physics, the gas, the stars, the feedback processes, all of which are complex and imperfectly modeled. More computation and better subgrid physics will eventually reconcile the simulations with observations. Second, dark matter is real, but it is not cold. A warmer, fuzzier, or self-interacting form of dark matter would cluster differently at small scales, potentially producing fewer small halos and allowing large structures to form in ways that better match the Webb data. Warm dark matter and fuzzy dark matter are both scientifically active alternatives, each with its own theoretical framework and observational predictions. Third, dark matter as conventionally conceived does not exist, and something fundamentally different is producing the gravitational effects attributed to it. 5 years ago, the third option was not seriously discussed at major conferences. It was the domain of a small number of theorists operating outside the mainstream. Today, it appears in papers submitted to leading astrophysical journals. The shift in tone is gradual, but it is real. The third option has not become mainstream. It has become discussable. That transition, from undiscussable to discussable, is where revolutions begin. Here is an assumption so deeply embedded in cosmology that most textbooks do not acknowledge it as an assumption. The universe, at sufficiently large scales, is identical everywhere and in every direction. Statistically smooth, statistically uniform, isotropic and homogeneous across the full observable volume. This is the cosmological principle. It is the foundation beneath the foundation. Einstein's equations applied to the universe as a whole can't be solved without it. Without large-scale uniformity, the mathematics of cosmic expansion becomes intractable. The entire machinery of modern cosmology, the Friedmann equations, the cosmic microwave background predictions, the structure formation simulations, runs on top of this assumption. It has never been directly verified. It is, in the truest sense, an axiom, chosen for practical necessity and supported by the general smoothness of the cosmic microwave background. Webb has been contributing indirectly, but persistently, to a growing body of evidence suggesting the cosmological principle may be more fragile than assumed. The clockwise galaxy rotation asymmetry, published and debated over the past several years, found that galaxies in one portion of the sky rotate preferentially in one direction, an effect that should be statistically absent if the cosmological principle holds. The Hubble tension itself carries a hint of directionality in some analyses, with the expansion rate appearing slightly different depending on which portion of the sky local measurements are drawn from. Then there is the large-scale structure. The Hercules Corona Borealis Great Wall, a structure of galaxies and clusters spanning roughly 10 billion light-years, is larger than the cosmological principle predicts should be possible. Simulations built on lambda cold dark matter do not produce structures of that magnitude. The South Pole cold spot in the cosmic microwave background remains unexplained after decades of analysis. The axis of evil, an alignment of features in the cosmic microwave background that appears to correlate with the plane of our solar system, has resisted dismissal. Each anomaly in isolation is manageable. Together they form a pattern, one suggesting the universe may possess preferred directions, preferred structural scales, and preferred asymmetries that a perfectly uniform cosmos should not have. If the cosmological principle is even slightly violated, the consequences for cosmology are not minor. Every inference drawn from the assumption of uniformity becomes suspect: the derived age of the universe, the inferred expansion history, the calculated matter density. All of these rest ultimately on the universe being statistically identical everywhere. Webb is not primarily a wide-field survey instrument. It probes deep into specific patches of sky. But the structures it discovers, the overdensities, the early clusters, the unexpected filaments, consistently suggest a universe more structured, more organized, and more directionally asymmetric than the cosmological principle permits. No one has declared the principle broken. The field is not ready to take that step, but the question is being asked with increasing seriousness by researchers who 5 years ago would not have entertained it. When an edifice's foundation shows fine cracks, you do not immediately conclude the building will collapse, but you do begin to study the cracks. Consider for a moment the engineer who spent 15 years designing a component of this telescope, retired in 2019, and watched the launch from home on a screen 2 years later. Consider the astronomer who wrote her doctoral dissertation on what Webb would find, using simulations grounded in lambda cold dark matter, and who is now 32 years old, sitting with data her dissertation did not predict. Consider the graduate students who enrolled in cosmology programs in 2019 because they wanted to work with Webb data, who were told the framework was mature, and their role would be to fill in its details. They are now confronting the possibility that the details do not fit, and that rebuilding the framework may be their generation's actual task. There is a particular human cost to scientific revolution that never appears in the papers. It is not the cost of being wrong. Scientists are trained intellectually, if not emotionally, to accept being wrong. The deeper cost is the cost of unlearning. A researcher who spent a decade developing sophisticated intuitions about how galaxies form under lambda cold dark matter, who built those intuitions into models and publications and lectures, faces a specific kind of loss when the data suggests those intuitions must be dismantled and rebuilt from scratch. Revision is, in one reading, the finest thing science demands of its practitioners, the capacity to update without fracturing. But it is also genuinely hard. Careers are built on frameworks. Grant applications invoke them. Teaching curricula encode them. Collaboration networks form around shared assumptions. When the assumptions shift, all of it shifts with them. The engineers who built Webb and did not live to see its first light are part of this story too. The telescope was first proposed in 1996. It launched in 2021. 25 years. The people who conceived it imagined it would confirm and extend the standard model. Some of them died before knowing what it would actually find. What it found was not confirmation. It found complication, productive, scientifically rich, intellectually transformative complication but complication nonetheless. The astronomers now working with Webb data are not a monolith of crisis. Many describe the experience with something closer to exhilaration, the electric sensation of being the first human beings to see something no one has ever seen. That feeling is real. It coexists sometimes within the same person, alongside a quieter anxiety about what the data means for everything they were trained to believe. Science advances generation by generation, each inheriting the models of the one before. The generation that breaks a model carries both the weight of that inheritance and the possibility of being the one that remakes it. It is a heavy thing to carry. It is also, by any reckoning, an extraordinary privilege. The universe is indifferent to the careers involved. It simply continues to be what it is, waiting for better instruments to read it more precisely. Webb is that instrument. And the people working with its data are, whether they sought the role or not, at the center of one of the most consequential scientific moments in decades. Before Webb, astronomers knew they needed a different kind of telescope. Not just deeper, but wider. Webb looks at extraordinarily small patches of sky with extraordinary sensitivity. Its field of view is a postage stamp. Its findings are transformative precisely because even that postage stamp keeps generating anomalies. Scale up. Survey the entire sky at comparable depth. The anomalies, if real, become undeniable. If they are statistical artifacts of sampling a narrow slice of the universe, that truth becomes undeniable too. Either answer resolves a question currently consuming billions of dollars of theoretical labor and decades of scientific effort. The Nancy Grace Roman Space Telescope is being built to provide that answer. Roman, named for the astronomer who was instrumental in creating the Hubble Space Telescope program, is designed with a field of view 100 times larger than Webb's. Where Webb sees a postage stamp, Roman will see a poster, at sensitivity levels that bring faint, distant galaxies into statistical clarity. Roman's anticipated launch in the late 2020s is not a routine step in a smooth scientific progression. In the context of everything Webb has found, it is a verdict machine. Its primary science program will measure the Hubble constant through multiple, entirely independent methods, including weak gravitational lensing, galaxy clustering across cosmic time, and Type 1a supernova distances across a sample vastly larger than any previous survey. If the Hubble tension is a genuine feature of the universe, and not an artifact of limited sampling, Roman will make that definitive. Roman will also survey the distribution of galaxy masses and sizes across billions of years of cosmic history. The early galaxy problem, the discovery that massive, developed galaxies appear too early and too fully, formed in the Standard Model, is currently based on Webb's observations of a relatively small number of fields. Roman will observe millions of galaxies across the same redshift ranges. If massive early galaxies are genuinely overabundant relative to lambda-cold dark matter predictions, the statistics will be unambiguous. If they are not, if Webb was simply sampling an unusually dense region, Roman will reveal that too. Dark energy is Roman's third principal target. The behavior of dark energy across cosmic time carries the signature of what it actually is. If dark energy is truly a cosmological constant, a fixed energy density of empty space, its influence should be identical at all epochs. If it is a dynamic field that evolves over time, Roman will detect that evolution through precision measurements of how galaxy clustering and cosmic expansion have varied over billions of years. The telescope is named for a person who spent her career constructing the infrastructure that made space astronomy possible, often working against institutional resistance. Roman herself argued for broad sky surveys over narrow, deep fields, a philosophy now embedded in the telescope bearing her name. Webb found the questions. Roman is being built to determine how seriously to take them. When it launches, when its first wide-field surveys begin returning data, the distribution of opinion inside cosmology will face a test that no individual researcher can manage through reinterpretation alone. The numbers will either hold up at scale or they will not. There is no way to read around a survey of hundreds of millions of galaxies. Roman is the next conversation, and it will be a conversation the universe must participate in directly. Return to the beginning. Christmas Day, 2021. A rocket rises from a launch facility on the northeastern coast of South America, carrying inside it a mirror composed of 18 gold-coated hexagons folded like a flower into a cylinder. The engineers watching from control rooms and parking lots and living rooms across 2 continents had spent, in some cases, the better part of their professional lives making that moment real. The rocket performed perfectly. The telescope separated. The unfolding began. No one in the control room that day knew what the telescope would find. They hoped, they modeled, they prepared. But the universe had not consulted the models. And so, 3 years later, we have this. A galaxy generating oxygen in the first 500 million years of existence. Oxygen that requires multiple generations of stellar birth and death to produce. Oxygen that should not have had time to materialize in a universe that young. Galaxies carrying the mass of mature spirals, already fully assembled when the cosmos was less than 5% of its current age. A constant of expansion that returns one value when measured against the ancient past, and a different value when measured in our immediate cosmic neighborhood. A preferred direction in galaxy spin that probability theory says should not exist. Stars that turned out to be entire clusters. Objects whose identity changed 3 times in 3 years as more data arrived, each revision more startling than the last. Taken individually, any one of these could be an anomaly, an error bar, a subtlety in the physics awaiting resolution through better simulations or more careful calibration. The field has absorbed individual anomalies before, but the accumulation sits differently. It is not one discrepancy. It is a dozen, arising from different instruments, different methodologies, different research teams on different continents, pointing at different phenomena, all converging on the same unresolved question. Is lambda cold dark matter, the model that has organized and guided cosmology for 30 years, fundamentally incomplete? That question sits at the center of the field right now in 2026. It does not have a consensus answer. Alison Kirkpatrick, who in 2023 described lying awake at 3 a.m, worrying that everything she thought she knew might be wrong, has not stopped working. She is still analyzing the data, still publishing, still contributing to a community that is, at its best, collectively honest about the limits of its own knowledge. Caitlin Casey and her collaborators are mapping the early universe's galaxy populations with increasing precision. Stefano Carniani's team is examining chemical signatures in objects that should not yet have had time to produce them. Peter van Dokkum, who called one of his discoveries a cosmic miracle, is still searching for more. These are not people in despair. They are people in precisely the condition science most requires, confronted by data that exceeds the reach of current explanation, unable to look away, unable to pretend the numbers resolve cleanly, unwilling to stop asking. The telescope that produced all of this is still out there, circling a gravitational equilibrium point between Earth and the outer solar system. Its gold mirror pointed at the oldest light in the observable universe, collecting photons that have traveled billions of light years to reach an instrument that cost $10 billion to build and 25 years to launch. It is transmitting home data that no one fully understands yet. That is not a failure. That is science at its most vital. The next instruments are already in development. Roman is being assembled. Ground-based observatories are readying their own contributions. Future space missions are in proposal stages, funded in part on the basis of what Webb found, designed to press further on the very questions Webb opened. The next generation of researchers is entering the field right now, some of them drawn specifically by the anomalies, by the sense that cosmology stands at a threshold, that the next decade of data could redraw the map of everything. The universe is not waiting. It has never waited. For 13.8 billion years, or perhaps longer, it has been exactly what it is, indifferent to the frameworks humans construct to describe it, continuing to evolve and expand and structure itself according to rules that the most powerful instruments ever built are only beginning to read clearly. Science is not the accumulation of answers. It is the refinement of questions. A civilization that can pose better questions understands more, even when the answers have not yet arrived. The James Webb Space Telescope has given us the finest questions in the history of cosmology, perhaps in the history of our species. The question of how the first light organized itself into structure. The question of what the universe is genuinely made of. The question of whether the cosmos we inhabit obeys a principle of uniformity, or whether it possesses directions, preferences, and asymmetries we have barely begun to measure. The question of whether the model that has guided 30 years of science is a foundation or a scaffold. None of those questions are closed. All of them are open. The data will keep arriving. The mirror will keep turning. And somewhere in the generations now looking upward, the minds that will answer these questions are already forming their first thoughts about the sky. That is not a conclusion. That is an invitation, extended by a gold mirror 1,000,000 miles from home, still cold, still patient, still listening to the oldest light in the universe as it arrives, photon by patient photon, across the dark.